In this video, we'll examine the concept of a random variable, the concept of a probability distribution, and we'll take a look at means and standard deviations of probability distributions. Let's assume that a family is going to have 4 children, and for the sake of convenience, let's assume a 50-50 gender binary, so that half the children will be boys and half will be girls, and those outcomes will be equally likely. Then you could take the time, if you were willing, to list all of the possible outcomes of sequences of girls and boys. It turns out there are 16 of them, because 2 to the 4th is 16. And if we just do a little counting, we'll let x represent the number of girls, let's say. And this x is an example of a random variable. It's a variable, the value of which is determined by some random process. So a family of 4 is either going to have no girls, or 1, or 2, or 3, or 4, and that total will be determined by each of the individual random trials of having either a boy or a girl. So if we look at the number of these outcomes that have no girls, we find there's 1 of them out of the 36. There are 4, sorry, out of the 16. There are 4 of the 16 that have 1 girl, which makes perfect sense, because if there's only 1 girl, it could either be the first one, the second one, the third one, the fourth one. Similarly, on the other end, if you're going to have 3 girls, you're going to have 1 boy, and that boy is either the first one, the second one, the third one, or the fourth one. There's only one way you're going to have all girls, and either by counting or simply by using the fact that these have to add up to 1, you quickly find that the probability that there will be 2 girls is 6/16. And it might be worth taking note of these numbers 1, 4, 6, 4, 1 and seeing if you have maybe encountered them somewhere before. So here's an example of a random variable, a list of all the possible values that it can take on, and then the probability associated with each of those values. This table, as we've constructed it so far, is a probability distribution. More specifically, it's a discrete probability distribution where you've got a random variable that can take on a fixed number of separate values, numerical values. You associate each of those values with the probability that the variable will take on that value, and you have a probability distribution. It turns out probability distributions have means, and the way to maybe start getting at that is to ask ourselves what the average number of girls would be if we had 16 families and their outcomes in terms of numbers of girls exactly conformed to expectation. So what would the average number of girls be across all those families then? Well, we would have 1 family with no girls. We would have 4 families with 1. We would have 6 families with 2. We would have 4 families with 3. And we would have 1 family with 4. And that would be out of an imagined total of 16 families. Now, we could just do the calculation. I don't think anybody would be surprised if it came out to be 2. But what I would like to do is do a little bit of rearranging of these terms here. I can first of all split this sum into separate terms, and I can also, within each term, rearrange a little bit. So, for example, I can take the 1 times 0 times 16, and I can call it 0 times 1/16. I can take the 4 times 1 divided by 16, and I can call it 1 times 4/16. I can take the 6 times 2 divided by 16 and call it 2 times 6/16. And I think you can see where this is going. Each of these terms is just going to be the value of the random variable times the probability that the variable takes on that value. So I'm going to have 3 times 4/16, and finally 4 times 1/16. And if I just add up the 16ths, I've got 4 plus 12 is 16, plus another 12 is 28, plus 4 is 32, and 32/16 is 2. So that should not be a surprise. We could then go on to make a definition of the mean of, or the expected value of a random variable, or equivalently of a probability distribution, and that's what we're going to do. So definition, the mean or the expected value of a discrete probability distribution, or equivalently of a random variable, is represented with this Greek letter mu, looks like a lowercase u. And what we did was we took each value that the random variable could take on, we multiplied it by the probability that it would take on that value, and we added them up. So if we were to make a formula, that's what it would be. You can also calculate a standard deviation of a probability distribution or of a random variable. If you imagine graphing this probability distribution and thinking about other probability distributions that you could potentially graph, they're going to be some of them quite spread out, some of them not so spread out, and just as we can measure spread in a data set, we can measure spread in a probability distribution. So we're going to say what the variance of a discrete random variable is, or of a discrete probability distribution is. We're not going to tell a very detailed story. We're just going to sort of accept the formula as it is. But as it turns out, we use the same symbol that we use in descriptive statistics world. We'll use a sigma. So definition, the standard deviation of a random variable or of a probability distribution is what you get when you take the squares of the values, multiply them by their probabilities, add them all up, subtract the square of the mean, and take the square root. Yeah, I know. But that's what it is. If you leave off the square root, then you have what we would call the variance of the random variable, or the variance of the probability distribution. And so that is the same sort of terminology that we were using with data sets. If you want to go ahead and look at how you might use a table to figure out the values of the mean and the standard deviation, as long as the numbers are reasonable, it's not so bad. The minute they get unreasonable, you want to start using the list editor in your calculator. But if I want to find the mean, I'll just take each value times its probability. So I just multiply all of these pairs. So I got 0 times 1/16, I got 1 times 4/16, I got 2 times 6/16, I got 3 times 4/16, I got 4 times 1/16. And if I add them up, as we said already, I've got 32/16, which of course is 2. So that would be the mean of this particular probability distribution. Then if I wanted the standard deviation, I would have to take a look at the squares of the x's times their probabilities. So I got 0 squared times 1/16, 1 squared times 4/16. 2 squared is 4, times 6/16 is 24/16. 3 squared is 9, times 4/16 is 36/16. And finally, 4 squared is 16, times 1/16 is 16/16. And some of these, of course, we could reduce, but since we're going to add them up, it might pay us not to do that just yet. So if I start adding these up, I have 16/16 and 36/16. Let's see, that's 52, 62, 72, 76, 80/16. Now that's not yet the variance or the standard deviation. All that is this part of the calculation, summing up the x squareds times the p of x squareds. So if I want to finish off finding the standard deviation, I'm going to take this 80/16. I'm going to subtract the mean squared, and we already know the mean is 2, and I'm going to slap a square root over all of it. And I'm going to grab my calculator and do this real fast. So 80/16 minus 4 is 1. Oh, how about that? And so the square root of 1, of course, is 1.